All right, let's get at the remaining considerations for Chapter 18. Which, now, by considering all we've done previously, with the addition of charge balance, and the possibility of setting charge balance equation equal to charge sum, give us all the tools we need to take any water solution apart in detail so as to be able to determine the QPSI, or quantitative inventory, for every species in the solution, every one whose presence depends on pH. That's pretty powerful. First, we can pick up with the consideration we put to you at the tail end of our last gathering, just to be sure you now understand this charge balance game and start to recognize when you can and when you cannot equate a charge balance equation to a charge sum. Here's what we left you with. I think it's question 1857. The charge balance equation for principal species, that's easy. Remember, in the charge balance expression, we have strictly charged particles, ions. And the principal positive ion in this system is hydrated aluminum ion, whose formula you see in the acid-base table. Ka for hydrated aluminum ion is 1.4 times 10 to minus 5. It's a little bit weaker acid than acetic acid. Sulfate ion, the only negative ion of consequence in this system. Charge sum, 0.60. You see this? Or are you mystified by 0.60? If everybody sees it, then we're all fine and we're moving on. Ah, everybody doesn't see it. For this solution, what similarity of sulfate ion? 0.30. What's the molarity of hydrated aluminum ion? 0.20. Last I checked, if I want to take a molarity of 0.20 and set it equal to a molarity of 0.30, the simplest arithmetic that I can do is to multiply the 0.20 by 3 and the 0.30 by 2. That gives me 0.60. Bingo. Source of number. How? Because I'm trying to write a charge balance equation. I want to write an equality between total moles of the principal positive ion with total moles of the principal negative ion. That's what I did. Do you recognize that in this system, as we've already noted, the sulfate ion molarity is 0.30? Is that all right? The aluminum ion molarity is 0.20. Is that all right? If I want these concentrations to be equal, so that I can write an equation which equates total moles plus to total moles minus, the simplest way to do it is multiply 0.20 by 3. That gives me 0.60, while at the same time multiplying 0.30 by 2, which also gives me 0.60. Now, total moles plus, when it's multiplied by 3, equals total moles minus when the minus is multiplied by 2. Remember we told you this yesterday. As quick as you can write. You write the molar concentration expressions using square bracket notation. for the positive ions and the negative ions. And what do you multiply these concentration terms by? Charge magnitude. That's it. So, for all species, hydrated aluminum ion. If hydrated aluminum ion loses H plus, it becomes this. And if this loses H plus, it becomes this. And we've already recognized, at least with the iron nitrate solution, that there is not going to be much difference between Ka1 and Ka2 for a hydrated metal ion acid. Now, we didn't ask the question why. Why is that? Do you remember that for a parent molecular acid, there's a huge difference between Ka1 and Ka2, a parent polyprotic molecular acid. Because the species produced by the first ionization of the molecular acid, beside hydronium ion, is an anion. It has a minus charge. And in order for that minus charge thing to react with water and create hydronium ion, from this minus charge thing, what do you have to remove? H plus. And the positive charge density of H plus is huge. And so it will stick strongly to a minus thing. Ain't that right, Coulomb? Well, when we deal with these hydrated metal ion acids, the parent acid for iron plus 3 is plus 3. The parent acid for aluminum plus hydrated aluminum ion is plus 3. And after the first reaction, now you've got hydronium ion and iron plus 2. I mean an ion containing an ion with a charge of plus 2 that contains iron. Iron's still in the plus 3 oxidation state for iron. For aluminum, you get this plus 2 ion. Hydroxyl, pentaquo, aluminum ion. Never mind the name. Formula tells us all we need to know. Oxidation state for aluminum is still plus 3, but now the charge on the ion is plus 2. Tell me, Coulomb, if I consider losing H plus from something which is plus, is that a lot easier than losing H plus from something which is minus? You're damn right. This is a favorable reaction from a Coulombic standpoint, because plus things repel each other. So these multi-positive hydrated metal ions have a natural tendency to kick out H plus and become less plus, because that's Coulombically favorable. There's one more reason why I argue that Coulomb's law is the most fundamentally important law in chemistry. Surely important when we're dealing with ions. So here, for all species, is the sum of total moles plus. 3 times this molarity, 2 times that molarity, and this molarity. And here is the sum of total moles minus. Do sulfate ion, twice sulfate ion molarity, hydrogen sulfate ion molarity, hydroxide ion molarity. And then I asked, can you set this equal to a charge sum? We've already seen why we can do that. And then I said, after you write the all-species charge balance equation, you think it's likely that this equation can be simplified? Sure. I can take out hydroxide ion, because this is an acidic solution. So whatever the hydroxide ion molarity is, it's less than 1.0 times 10 to minus 7. Furthermore, if I ever need hydroxide ion, if I got this, can I always get hydroxide ion? Hell yes, KW permits that. So who needs hydroxide ion? How about hydrogen sulfate ion? You think it's fair to throw that away? Because the only way you can get hydrogen sulfate ion in this system is if this reaction proceeds left to right prior to the establishment of equilibrium. Now, by now you know that by definition, the equilibrium constant for this reaction is called Kb sulfate ion, isn't it? You know what the value is for Kb sulfate ion? Look at the table, acid-base table. This a big number? Not lately. Not ever. This number tells me that the ability of sulfate ion to behave as a base in water solution is pretty feeble at best. In 46 laboratory, at the tail end of assignment 2, we told you, take the laboratory sodium sulfate solution, which I think is half molar, and observe pH. How many of you remember doing that? What kind of pH value did you get?
I think 5.
5 for a basic solution? I think something's wrong. You better clean your glassware. What'd you get?
I don't know if I remember, but
You don't? That's terrible.
I was on the basic side. You know that?
On the basic side.
I don't remember exactly about it.
Anybody remember the gee whiz value? Half molar sodium sulfate solution. Close to neutral. With bronthymol blue indicator, you'll get a blue-green color. Remember bronthymol blue? pH 7.0 is green. 8.0 above is blue. Now you're seeing a green-blue color. So you know the pH is less than 8.0. It's only about 7.3, 7.4. Sulfate ion is a damn weak base. So this reaction, practically speaking, isn't going anywhere in here. You can forget hydrogen sulfate ion. But I can tell you, if you want to calculate the molarity of hydrogen sulfate ion in this system, you can now do it. And you just keep this in. Now, I put question marks over these molarities. I put question marks over these molarities because unlike the iron nitrate solution, which we considered last time, these molarities, the molarities of these species may be negligible in this system. If I make that statement on a quiz and I tell you to tell me why, what will you tell me? Here's the question. In 100th molar ferric nitrate solution, we cannot neglect the molarities of quote-unquote iron 2 and iron 1. Remember, those are the things which we use as shorthand formulas for what you get after quote-unquote iron 3, which is really hexaaquo, iron plus 3 reacts, and then makes monohydroxyl pentaaquo, iron 2 ion, and then monohydroxyl pentaaquo, iron 2 ion reacts with water and makes dihydroxyl tetraaquo, iron 1 ion. Can't neglect the species, the concentrations of those species in 100th molar iron nitrate solution. Well, these are the parallel species for this hydrate aluminum ion system. And I'm saying you probably can neglect these, but you can't do that for the iron system. Tell me why. We've been through this time and again. Now put it to use. What does ionization extent depend on, once again? Ka values and?
1 over
And 1 over m sub I. How dilute is the system? This is 10th molar. That's 10 times more concentrated than 100th molar iron nitrate solution, isn't it? And Ka1 for iron, hydrated iron, is 4.0 times 10 to minus 3. Ka1 for hydrated aluminum ion is 1.4 times 10 to minus 5. I'm reading these values right off the table because I told you, I keep the table in my noggin. You will too if you ever get to do what I'm doing. And you'll say, what a pleasure. I can see the table whenever I want. You see a rather large difference in these K values? The far bigger K value is that for hydrated iron plus 3, which means its ionization extent relative to hydrated aluminum ion is a hell of a lot greater. So it's not an unreasonable bet that for 10th molar aluminum sulfate solution, which is fairly concentrated, the ionization extent of this is pretty small, which is why these concentrations may be negligible. You'd have to do some arithmetic to find out for sure, and I don't know right off the top of my hat. But I know what I have to think about to find this out. I know the chemistry of the system, and you know now. You want to tackle any of these problems? You better pay attention to the chemistry of the system first and foremost. That's where the answers lie. All right? Another question for our hydrated iron containing solution, our 100th molar ferric nitrate solution. We laid foundation with our last gathering for calculation of hydronium ion concentration for this solution. Ka1, Ka2, material balance, charge balance. That gives you the 4 equations, simultaneous independent equations composed of the same set of 4 unknowns, which means now you can solve it. You learned that in algebra class. Now what would you do if you wanted to solve that? Would you tackle it with rigorous algebra? If you try it that way, you better have a hell of a large supply of aspirin, because you're going to get some nasty headaches. But if you tackle it from a chemist's perspective, it's not that difficult at all. Give me your pocket calculator, some scratch paper, and most importantly, this computer functioning, and we'll have at it, and won't take long at all. I'm going to tackle it just like I tackled way back at the end of chapter 17, when we had the ammonia and nitrogen and hydrogen equilibrium. And we recognize for the ammonia, nitrogen, hydrogen equilibrium system, as we discussed it, if you expanded it algebraically, you'd get a 4th order polynomial. That's a mess to tackle from a rigorous algebra standpoint. You're going to get the same thing here. I'm going to fool around with that. So back at the end of chapter 17, when we wrote our equilibrium constant, we had looked at this equilibrium constant expression expressed algebraically. We says, let this damn thing talk to us. Tell it what it means. First thing we did was to realize these are concentrations contained in this term. They can't be negative values. It can't be 0. This is an algebra class. This is chemistry class. Same thing applies here. And what I would do in this case is, given that I want to calculate the hydronium ion concentration, I'm going to see what kind of hydronium ion concentration value I can expect for this system before I start doing any extensive calculation. For starters, I know at the minimum the hydronium ion concentration is bigger than 1.0 times 10 to the minus 7. Nothing fancy about that. It's an acidic solution. The solution is 100th molar. So I know this thing isn't going to give me a pH on the order of 1.0. Has it got enough acid solute to do that? And then to get a much better handle on the correct hydronium ion concentration for this solution, I'm going to calculate the minimum possible value for the hydronium ion concentration. In fact, what this will be is the lower boundary value, because this calculation will give me a hydronium ion concentration which has got to be smaller than the true hydronium ion concentration for the solution. It's got to be smaller. But it can't be smaller than this value. So I'll write it as hydronium ion concentration min. How do I do this? I pay attention to Ka1 for iron plus 3. Which means I'm looking at this equilibrium expression. Now what did we realize is the difficulty in calculating the correct hydronium ion concentration for a hydrated metal ion containing system like this. You also have to pay attention to Ka2, don't you? That means Ka2 is contributing to the solution hydronium ion concentration. So to get this hydronium ion min, I'm going to forget Ka2. I'm just going to look at Ka1, and I'm going to apply to Ka1 this recipe. And notice how I put quotes on this, because this is not a true equality. I know the hydronium ion concentration, which I calculate by applying this to Ka1, will be smaller than the true hydronium ion concentration for the system, but I'm getting a lower limit boundary value. Well, there's Ka1. M sub I is 0.010. So hydronium ion concentration min, by application of this, will be this, which is this. So I know the hydronium ion concentration for this system. I'll write thus H3O plus true. The actual hydronium ion concentration for the system is greater than 6.3 times 10 to the minus 3. Right? And less than 1.0 times 10 to the minus 2. I got this thing in a good box already, don't I? What?
How did you come up with that 0.0, the concentration times
This?
Ka? No, the concentration times Ka. Yeah, the number.
By this. This is the arithmetic I did. I think what you're really asking me is, how can I state that this is valid to give me the hydronium ion concentration min? I told you why. Because with this arithmetic, we're saying forget the second ionization, but we know the second ionization goes, and it goes measurably, which means the second ionization is also adding to the hydronium ion concentration. So whatever the hydronium ion concentration is for the solution, it's got to be bigger than this number, because this is what I got just by considering the first ionization.
How do you know it has to be less than 1.0 times 2?
See this label? If all the hydrated iron reacts, all of it, then the first equilibrium doesn't even exist anymore, does it? Which would give us a hydronium ion concentration of 0.010, which I wrote there in significant figure form, right? How about that? I mean, we haven't done anything fancy, and look at this. We know we can get the hydronium ion concentration to 2 sig figs. And I got this thing in a pretty small box already, haven't I? It's in here someplace. 6.4, 6.5, 6.6, 6.7, and I'll keep on reading until I get to 10.0 times 10 to the minus 3, because that's this. That's in there someplace.
Okay, so for coming up with the minimum H3O concentration, you assume that the initial molarity minus the concentration of the reacting for x squared over mi minus x.
Huh.
You assume that mi minus x is close to mi.
Here?
Yeah. For
Maybe I did some bad arithmetic here. Let's see. Let's check that. I mean, you may have a point there. So I'll get, let's see. No, this is no good. No good. Up. Let me write this over. My fault. I'm glad you said that. To solve correctly, must keep x in denominator. So, what we found out by doing this is that the hydronium ion concentration considered by this is not this big. My fault. Okay? We got to keep this in here to do this. All right? So what you're really operating on is, I wrote it here. Solve this thing for x. It won't be as big as this. My apologies. I was in such a hurry to show you this that I messed up the arithmetic. Stupid me. 100 off for me. You can have the 100. Because we'll divide it amongst all of you. Okay? But you know what to do now. That's what counts, is knowing what to do. My fault. I'll do the arithmetic properly and report to you the correct value next time. But I know the correct value is less than 6.3 times 10 to minus 3. How am I going to solve this? I'm going to try my ionization extent guess. All right? If I pick 50%, this will be 5.0 times 10 to minus 3. All right? And 5.0 times 10 to minus 3 is a little bit bigger than this, isn't it? So I know ionization extent less than 50%. 40% ought to be pretty close. Let's see. 40%, that'd give me 0.006 and 4.0 times 10 to the minus 3 squared up here. Let's see, 4 squared, 16. 16 divided by 6. 3 would be a little bit bigger than that. All right, you know what to do. You do the arithmetic. All right? My fault for messing it up, but good that you called my attention to that. In any case, let's move along. Equating charge balance to a charge sum. We mentioned this last time, and we've showed you a couple of cases where this has been achievable. Okay? Now then, considerations you have to make. Is the solute ionic like this? Like aluminum sulfate? And if the solute is ionic, does it contain a spectator ion? Well, certainly here. Okay? Nitrate ion. So right off the bat, you know for this solution, the charge sum is 0.030. Because you know the nitrate ion is in there, you know it's the principal negative ion, and you know that it doesn't do any chemistry while it's in there. So you know the nitrate ion molarity, which is part of the charge balance equation, is 0.030. Enough, done. Because the molarities of anything else in there that's minus, like we talked about hydroxide ion, which for that system is the only other thing in there that's negative, is less than 1.0 times 10 to minus 7. You add that to 0.030, you're not changing anything arithmetically, right? So, now then, how about aluminum sulfate solution? You think this charge sum is legitimate? We told you how we got it. Now we're asking the question, is this charge sum legitimate? Now, for hydrate aluminum ion versus sulfate ion, Which of these ions will have its concentration, initial concentration, the m sub I value, which again for hydrated aluminum ion is 0.020, for sulfate ion, 0.20, pardon me, and for sulfate ion 0.30. Which of these ions will have its concentration altered to the greatest extent when it's put in solution? Because it's going to do some chemistry in the system. Which one? Hydrated aluminum ion. That's correct. Why? Because Ka for hydrated aluminum ion is 1.4 times 10 to the minus 5. And Kb for sulfate ion, we got over there, don't we? 8.3 times 10 to the minus 13. So sulfate ion isn't going to do anything, practically speaking. Aluminum ion will, but sulfate ion won't. So practically speaking in this system, because the Kb value for sulfate ion is so damn small, we can treat it like a spectator ion, which allows us to write this charge sum for that solution. Because the sulfate ion molarity isn't going to go anyplace. If you don't believe it, if you think that with this tiny little Kb value, the sulfate ion might do something, sit down with scratch paper and wrestle with the arithmetic. You'll find out it doesn't go anyplace. The sulfate ion molarity will remain the same as its initial molarity. So, these two cases, the aluminum sulfate solution, the iron nitrate solution, are each examples of cases where our charge balance equation can be set equal to a charge sum. Now then, what if the solute is molecular, like sulfuric acid solution? This becomes more difficult, because you can't, although writing the charge balance equation for sulfuric acid solution, in fact we're going to do it in a moment, you can't set that equal to a charge sum unless you know ionization extents. Let's look at an example of such. Let's look at an example. Well, since we talked about that, let's do that one right now, by golly. On your paper right now, write all species CB for H2SO4 solution. Write it on your paper right now. The all species CB. Not a difficult task. You get this? How many got this? You know every water solution got hydronium ion and hydroxide ion. And you know this thing, sulfuric acid solute, puts hydrogen sulfate ion in there. And if the hydrogen sulfate ion does anything, it's going to convert to sulfate ion. And more hydronium ion. So there it is. Now the question is, can I set this equal to a charge sum? And, since we've looked at this consideration previously, you think I can legitimately simplify this relationship? You think it's fair to do this? Sulfuric acid solution unless it's exceptionally dilute, the hydroxide ion concentration, whatever it is, has got to be a good deal smaller than 1 times 10 to minus 7. Whereas the hydronium ion concentration is a good deal larger than 1 times 10 to minus 7. Like 10th molar sulfuric acid solution, hydronium ion concentration is at least 10th molar. 100th molar, at least 100th molar. 1000th molar, at least 1000th molar. 10 to the minus 4 molar, at least 10 to the minus 4 molar. Remember? Hydronium ion concentration for a sulfuric acid solution cannot be smaller than m sub I. All right? Can I set this equal to a charge sum? How about 10th molar sulfuric acid solution? What do we know about the charge sum value? What do we know about the hydronium ion concentration for 10th molar sulfuric acid solution? We know that it's bigger than 0.10 molar, but it's smaller than how much? 0.20 molar. So you got the charge sum in the box, but you don't know what it is. For this, bigger than 0.10 molar, less than 0.20 molar. But what is the exact value? You got to calculate the ionization extent for hydrogen sulfate ion to know the exact value. Now let's look at question 1860, a very dilute solution of sulfuric acid. Consider one times 10 to minus 5 sulfuric acid solution. At this m sub I value, what do you think is the ionization extent for hydrogen sulfate ion? What? What? 100%. 100% for sure. If you're mystified by this, sit down with some scratch paper and do some arithmetic. Indeed, if you do these things that I ask you to do, this stuff will become alive to you. It will show you the things that I'm saying to you. So for this solution, I can write the charge sum. What is it? That's it, all done. There's my charge sum. This is sulfuric acid molecule reacts with water 100%, and in this case, the hydrogen sulfate ion is going to react with water 100%. So, charge sum's double that.
Why didn't you cancel out the HSO4 minus?
Why did I cancel it out?
Yes, sir, like you did with...
In sulfuric acid solution? Oh no. That's a high concentration species. Unless the hydrogen sulfate ion reacts to an extent of 100% like it does for the very dilute sulfuric acid solution. Remember, in this solution, the molarity of hydrogen sulfate ion comes from the reaction of sulfuric acid molecule with water, and that's 100%. In aluminum sulfate solution, the hydrogen sulfate ion comes from sulfate ion reacting with water. And as that Kb value for sulfate ion tells us, the ability of sulfate ion to react with water is pretty damn feeble. Now, let's finish today with looking at this solution. Notice that this is a solution of an ionic compound, isn't it? Ammonium cyanide. 10th molar to 2 sig figs. There's the charge balance equation. Simple charge balance equation. One main positive ion, ammonium ion and hydronium ion. One main negative ion, cyanide ion, whose formula I like to write like this, because the negative charge is on carbon for the cyanide ion. And hydroxide ion. What's the charge sum value? Got to be careful. Here's why you have to be careful. For this system, as our acid-base chemistry tells us, the main acid-base reaction is, in this system, between ammonium ion and cyanide ion. Because ammonium ion is the strongest acid in high concentration in this system, and cyanide ion is the strongest base in high concentration in this system. Products, HCN and ammonia. Now notice, this is going to have a significant impact on charge sum if this reaction goes to any appreciable extent before equilibrium is established, because these products don't have charges. If these products were also ions, we could still write the charge sum. Because if you turn ions into ions, who cares? They're part of the charge balance equation. But this turns ions into molecules. It converts charged species into uncharged species. Well, what do you think is the extent of this reaction left to right before equilibrium is established? Now, I've shown you the K value on the board, but I want you now to take a look at the acid-base table. Take a look at the acid-base table. Are you looking at it? What's Ka ammonium ion? 5.6 times 10 to minus 10. What's KaHCN?
6.2 times 10 to minus
6.2 times 10 to minus 10. Do you find an extreme degree of similarity between these Ka values?
Yep.
What does that mean about this reaction going left to right before the equilibrium condition is established? What does that mean about this reaction from an extent standpoint? Approximate extent. Because if you do the Kb value comparisons, you're going to get the same thing. The Kb value, cyanide ion and ammonia, very close to each other. So what kind of gee whiz extent does this thing proceed? 50%. That's a large extent, daggone it. And you can prove that by calculating K for this system. Here's how you calculate K. We'll do this kind of stuff extensively in Chapter 19. The K value is 0.90, which keeps with our assessment of the significant appreciable extent of this reaction, which means for this system, can we legitimately write a charge sum? No! Because this reaction is not only going appreciably, it's converting charged species to uncharged species. So all we can say for sure, without doing further arithmetic, is that the charge sum for this charge balance equation compares how to 0.10? It's a good deal smaller than 0.10. That's what we can say. And if you want, you can now do arithmetic to find out just what the charge sum value is, because I gave you the K value for that reaction. But don't fret on it, because we'll look at that in far greater detail next time, when next time we wrap up Chapter 18 finally, and then go back to Chapter 19.